Today I'm going to be talking about hybrid steel and timber systems. The last presentation was a really good overview of all the different ways that we can be looking at hybrid structures. My talk is specifically going to be talking about mixing structural steel with mass timber, talking about a couple of recent projects of ours. But before I get started, I like to do a little bit of an educational standpoint for the audience about what do we mean when we say hybrid and composite, because it depends on the scale you're talking about. So when we talk about composite elements, individual structural components within a building, we're talking about things like composite metal deck. So you've got a corrugated metal deck, it's got some deformations on it, you pour the concrete over it, they're bonded together and interlocked to form one composite slab, where the metal deck becomes a tension reinforcing. On a structural steel beam, we could put shear studs on there so that that concrete topping that we put over our metal deck is now linked to that steel beam, making a T shape that allows us to get more efficiencies out of our structural steel framing. These are really commonplace systems. But then thinking beyond just an individual element, we have to think about buildings. And here's where we have systems in parallel that might not actually be resisting loads together, but are both supporting the building. So in this example, which is a very common typology, is structural steel framing in the office component of a building, so steel columns and long span steel framing, and then a central reinforced concrete core. You see this in a lot of different buildings, and it's done primarily for economy if a reinforced concrete core happens to be the most effective way to support your building in your market. So the concrete core and the steel columns aren't resisting the same load, but they're together in the same building. I like to diagram this out in a bit of a triangle. For a long time, when we're talking about tall structures, we talk about steel and concrete. How composite is it? Are you putting concrete columns with steel framing and a concrete core, and where you're falling on this spectrum? But now that timber has really grown up in this space, we have to think about it as this tripod and where you fall in the areas within it. Well, the reasons why we might select steel, timber, or concrete really depend on what that material is good at. They all have natural advantages and disadvantages. So for example, timber, as we've all discussed, is very lightweight. It's got high compression and bending strength, but it has moderate ductility. Concrete, on the other hand, is very heavy. It's really only good in compressive strength. It needs to be reinforced with rebar to get bending or tension strength. And it also has moderate ductility. Whereas structural steel, on the left-hand corner there, is also a very lightweight material. It's got high tension, compression, and bending strength, and very high ductility. And that's why in a lot of these presentations that you've seen today, structural steel is being used for the connections, because that's where all the magic's happening. That's where the rubber's meeting the road. So you need a high-performing material to get that job done. So when we're building these buildings and we're trying to select these different materials and where to put them, we have to consider those issues. This project shown on the right-hand side here is the Long Beach Library that's under construction right now. It's part of a larger project that our firm SOM is putting up. The project itself uses structural steel columns and structural steel braced frames for the seismic resistance, and then it used glulam framing for the girders, joists, and decking. And by doing that, you get this nice exposed, warm timber frame, but you get the high seismic resisting system and ductility of the steel. Both systems are prefabricated, so they go up fast, as other presenters have discussed. And both systems are very lightweight, so there's a huge benefit there that I'll talk about in the next couple of slides. So what is our typical approach? Well, the typical approach is let's use timber where we can use timbers. That means the floors. So we're saving a lot on the weight associated with that system, and it gives us our acoustic and our fire resistance naturally with the exposed material. We then typically are looking at a lot of buildings that are using steel as a seismic resisting system, carbon-12, a good example of that, using buckling restrained braces. On this project, we're just using specially detailed steel braces, not BRBs. And then lastly, whether you choose steel or timber columns really depends on you. What is the building all about, and what are you trying to do? Here's a rendering of what the library will look like when it's completed later on this year. A nice frame that's open. It's got a lot of materiality and variability to it. That's going to be a nice feature for the new Civic Center. Here's a view of the interior, looking at the atrium. Again, exposed glulam framing, and then we have this structural steel that's just painted white. Now what we actually did in this building, because we needed a little bit of a fire rating on that steel, is we actually filled it with concrete. And that gives you enough of a thermal mass so that we didn't have to fireproof these columns. So that paint that we're putting on the columns is just a conventional paint. It's not an intumescent or anything like that. But it gives you a nice bright open space that's very good for learning and very good for the occupants. Here's a section looking around the site, and now you can really see these issues at play. What actually was there before was this 2-story parking garage in the basement, plus landscaping over the top and some miscellaneous 1-story structures on top of it. So when we got into the competition phase of this project, we said, you know what would actually help this project out a lot is if this building didn't require foundations. So what we actually did for this project is went in and took away all of that existing landscaping and moved it to a new park that's going to be adjacent, demolished those 1-story structures, demolished some of the structures within the basement, and then went and put up this lightweight 2-story steel and timber framed library on top of that existing structures. So those foundation elements down there, they just stayed. So by using these lightweight materials in combination with each other, we're actually able to reuse the foundations as well. You can see elevated inside here are the steel bracing, and then you also see this layer hatched down below here, which I'll talk a little bit about now. We had to make up for the elevation differences with the new master plan and the new landscaping plan. So what we actually did there is piled in geofoam. So geofoam is a high load carrying capacity foam that can basically displace volume. So what you see there, which looks like a 4-foot solid block of concrete, is actually mostly foam that's just encased in a thin shell of concrete. You see the structural steel columns going up with the hangers, and then the glue lam framing goes on top of them. You can see the concealed hangers on the inside. Again, we want to keep those protected because of fire to get the enhancement that we needed out of it. These were taken about, I think, a month ago, so now the second level is going on top of it, but you can see the steel bracing partially painted on there. Again, zooming in on this. Now, what's kind of clever with structural steel is because you can minimize the sizes associated with it, we're actually able to kind of conceal that steel beam, that steel tie beam that ties it into the columns up above, hidden up inside the timber, so you see these well-detailed steel braces kind of just disappear into the timber frame, which just gives it a nice look. And then looking from the top, this is looking across the atrium now from one side of the steel bracing to the next side of the steel bracing with the glue lam framing going in and some steel around the outside. So I would say this project is really a prototypical way in where we try to mix steel and timber for maximum performance. In this case, again, because of the limited seismicity available to us, we wanted to get a high ductile system. We selected structural steel, but then we also want to use the timber for the warm and for the sustainability values, and combining those two together gives us a lightweight system which could reuse foundations, and that's a very, very sustainable approach. The idea of combining materials in a hybrid solution makes a lot of sense, and it's a subject we've studied a great deal in the last 5 years. We've put out now 4 research reports on how to use mass timber for high-rise buildings. The report with the AISC on the right-hand side is just the latest of those 4. And so if you got your phones up, you don't really need them. Because what's going to happen here is if you go to our website, som.com, under ideas and research on the left-hand side here, you can go ahead and download all 4 of those reports. The one I want to talk to you now about in more detail is a steel plus timber system that we did in conjunction with the American Institute of Steel Construction. When I was talking to them, and we've got a lot of friends over there, I said, you know, look, we've got these 2 materials, they've got these natural benefits together, and we know mass timber is only going to get more affordable as we go forward. Let's try and explore reasonable ways that we can combine these materials so that we can find a way to get lightweight, more sustainable buildings. So we conducted a research study taking a look at a benchmark building in reinforced concrete and tried to replace it with a structural steel and timber system. Now, this is just looking at a structural analysis model. It's a real building in California that's been built and is completed. You can go find it online, but let's not get distracted by all of the fancy claddings and things like that. It's an 8-story residential building, very conventional system, post-tensioned concrete, and a wide column grid that allows us to get the units that we want. Here's the unit layout in the building. The typical column grid on this building is 27'6" by 32. And so when you look at a building with column grids that big, these are high-end units that are very large and able to get a lot of different configurations without columns in the middle. And so it's color-coded from one unit to the next, the orange to the green, and so on and so forth. And now I totally agree with what our previous presenter mentioned in terms of flexibility. We don't want to have load-bearing walls all over the place because it hurts the flexibility and the future flexibility of our structures, which is ultimately why they would come down. And so it's agreed that you want to try to avoid load-bearing walls, but if you can eliminate them altogether in the floor plate, it's much better, because if I'm a super rich guy and I own this unit and I want to buy this unit and combine the two, maybe I want to take down those party walls and just blow the whole thing open. So if there's a party wall there that avoids or makes it much more challenging to combine units in the future. This is the column grid and the structural layout, really. That's it for the benchmark building. Post-tension concrete, 8-inch flat plate. You can see it's got a 27'6" dimension in this over here, and this is 32 foot going between there. On this we have about 6 foot to 8 foot cantilevers, so there's only 1, 2, 3 column grids through the entire building. That's stripped down. That's pretty efficient. That's kind of the best you can really do with concrete. And so the reason why we selected that is because when we develop our system using steel and timber, we want to be able to show that we're not getting a false positive. Because if you go in with a straw man argument and you say, look, I'm going to benchmark against this concrete building and it's just terrible, and you're just like, oh yeah, this is no big deal. Of course we can do this in steel and timber. You haven't really proven much. So you want to go against the best to prove that you've got a good solution. This is our proposed framing plan using the steel and timber solution. And what we're trying to do is get the same values, not exactly the same column grids, but the same values. So the biggest thing with the column grid is maintaining a 27'6" column grid dimension so that we can get that same unit size. If you come in with your system and says you got to change your units because the column grid's tighter, it's not going to fly. But we did add a column grid in this direction and avoid those cantilevers because it doesn't impact the unit layouts. And then we've got a braced frame core here and a braced frame core there. An elevation would look like this. 2 remote cores and then just a field of columns at roughly 24 by 27'6". You can plan whatever you want in that dimension. And in fact, actually, if market demands change and you want to take some of your 1-bedroom condos and turn them into 2-bedroom condos late in the game, you can do that with just an ordinary column grid. You can't do that if your load-bearing structure is already defined. You can't change downstream. Another thing I wanted to mention about these core elements and what you would select. Now, we just drew in here some eccentric braced frames, but there's no reason why you couldn't also use buckling restrained braces or anything else. It really just depends on your specific project and what is most economical and what makes sense for you. Another thing you should keep in mind is when we're talking about resiliency, the buckling restrained brace option is also a really great option because it's also to some degree self-centering. We talk a lot about rocking walls and the energy dissipation that happens. Well, in those energy dissipation, there's connectors that you replace and you put back, and it self-centers. With a buckling restrained brace, if you design the rest of the boundary structure to remain elastic, when you cut that out, that elastic energy in the frame snaps back and moves back. So after an earthquake, you can just cut those BRBs out. It's going to recenter itself, put the BRBs back in, and it's self-centered. It just might take a month or so. It's not going to happen instantaneously, but still a very resilient solution. So here's a zoomed in plan so we can really start talking about the details and what we're trying to achieve. We have 4 column grids, 1, 2, 3, 4, that run down the length. Those column grids support timber floors that span up and down. You can see we've located these column grids so that we can get right adjacent to the main MEP openings. And that's what's really dictating where you can set these column grids. So in doing this, we've got all the same flexibility as before. You've got no internal bearing walls in your units, and those columns are tiny. They're W10 columns, so a 10-inch by 10-inch steel column. And part of this talk is about when we go taller, and I'll mention that a little bit further, but with structural steel, if you go taller, your column's not growing size, it's not getting bigger in size, the plates are getting thicker. So you don't get these big, enormous columns that are intruding in your room. So it's a nice solution. There's a rendering of the system right there. So the system now, as I can explain it a little bit better, has 4 column grids, you're only seeing 3, with structural steel beams running down the way and cross-laminated timber spanning in between those steel beams. You're seeing steel columns at a field here with a fancy little steel connection that I'll talk about. But the rendering kind of looks a little bit wrong because it's a structural steel beam, but I don't see a downturn that's happening into the space. What's happening here? Well, what we want to try to do, again, is to compete with concrete. We need to try and understand why it's successful. And one of the reasons why it's successful is that flat plate is easy to coordinate surfaces. It's easy to wrap things around. So what we actually want to try to do using structural steel and timber is to get the same type solution. So what we've done here is we've upturned that steel beam and we've concealed it within the thickness of a composite timber and concrete floor. Those are the details. On the left-hand side is a little structural steel frame. It is an asymmetric steel beam, so it's got a T with a bar on top. Then you drop the cross-laminated timber floor planks directly down onto the bottom flange of that steel beam, routed out on the bottom, of course, so that it sits flush. And then we go ahead and we pour a composite concrete topping slab over the whole thing. We do the composite concrete topping slab because it gives us our acoustic requirements that we need for residential construction. It enhances the fire resistance, which makes it a viable solution for a very tall building. And then it also gives us our seismic diaphragm. So in this solution, it's actually steel and concrete that are giving you your entirety of your steel or of your seismic resistance. And in doing so, it's simplified the approvals process as well as having a flat soffit condition. So how is this working? How are we making these things work as a flat plate? Well, part of the issue is how you connect it. We don't want to leave any stiffness on the table. So what we want to try and do is make everything connected, monolithic, and continuous. This was a recent test that we did on composite timber framing at Oregon State University a couple of years ago now. And in this test, we were looking at composite timber frames for high-rise buildings once again. And the way we were able to get these long spans, this is 24 feet from here to here, is by making that slab continuous. Instead of allowing it to rotate at the supports and sag in between, we lock them in. So if I could diagram the forces in the slab for you, you would find something like this. The actuator loads are coming down here. We've got our arrows on the ends that are holding down the ends, modeling the mass of the adjacent bays. And then we have our reactions at these beams. The thing that allows us to get these continuous floor spans and to get the spans that we want is actually that dotted red line in there that is a bit of reinforcing in the topping slab. So the Europeans really developed a lot of this timber concrete composite technology. But one of the things that a lot of them looked at were just simple spans and keeping that concrete in compression. But when we do a reinforced concrete flat plate, it's about making it continuous over the supports. And we do that by reinforcing it properly. So we do the same thing in this timber concrete composite solution. So what are we trying to do for our steel and timber solution? Same thing. To get longer spans without adding material, you need to have continuous connections. So the red lines there show the floor spans of the CLT decks. They're reinforced over the blue lines, which are the steel beams. Then the blue lines themselves are connected through the steel columns to make continuous beams as well. And so here you can really see what we're trying to do. We're trying to make a two-way flat plate. But instead of it being a reinforced concrete two-way flat plate, it is a steel and timber hybrid two-way flat plate that allows us to get these big column bays without downstanding our beams. Looking at the details again, now that you understand a little bit more about what we're trying to do, you've got a structural steel column, you've got a composite timber floor, and they're mixed. And really what we're trying to do is get continuous behavior. So all the way on the left-hand side, when you're looking at that steel column, it's bolted to the face of the steel column, the end of the beam, so that red dashed line can transmit tension through the column. That blue dashed line is really transmitting compression through the column through bearing on it. At the floor connection, we've got the red dashed line for continuous tension over the top with the rebar, and then we've got continuous compression on the bottom side of compression through that concrete connection. So in doing so, you've got continuous two-way connectivity, and that's how you can get such long spans without downturned beams. Here are the steel details available, again, if you download the report. You've got a steel column, stiffened, of course, with an end plate connection just 4 bolts. It comes into the field and you make those beams a little bit short, so when you crane everything in, you jam in some shims to make them good for erection. We talked a little bit about that in the previous presentations about how you get that tolerance. So by giving those end plates a little tolerance, you can get it all in and you bolt it together to make a monolithic section. And then there are the steel details. On the left-hand side is a perimeter condition where we have a reinforced concrete cantilever from these asymmetric beams. And on the right-hand side is a typical interior condition. And this is where you really have a balanced condition where you've got a steel beam, CLT floor sitting on it. It's upturned with this massive steel bar concealed in here for the steel that we need. So in doing all of that, we're actually able to get this flat soffit condition. Some more details on the left-hand side is just timber plank to timber plank, simply screwed together for the temporary condition because the reinforced concrete topping slab takes all of our diaphragm. And then the transition into the cores. Now for this project, we selected an 8-story building because we thought it was the right benchmark, but we're also talking about taking the scheme to unlimited heights. And one of the techniques that we can do to try and enhance the system is only use timber where it's going to be exposed. So inside the cores, where you have a lot of MEP penetrations, you have fire egress issues, why push it inside the core? Go ahead and use a composite metal deck for enhanced fire performance and enhanced ability to get large penetrations and frame them out. So that's it. That's the proposed system. We're primarily focused on the gravity frame, where then the lateral load resisting system is plug and play. Now that you see the typical framing system, you kind of understand how this works, but more importantly, how we're using the structural steel frame for the maximum benefit and the timber for its maximum benefit in terms of aesthetics and lightweight behavior for this building. And the rendering's pretty nice. You just have these steel beams that are running along. Now, there's going to be refinements that are going to need to be done before the system is being used on a large scale. Does that steel beam need to be exactly flush with the CLT, or can it stick down an inch? Well, that's for you to work through and look at your coordination details with your team to try and understand if you really need that or if you can allow that with your services to pass through. What are the economics of this? Where's your local market conditions? Can you deliver something like this? Which is why in the report we provided this little section about conclusions and a worksheet. What we did here is we tried to go after a building with very big column bays, 27'6" for a unit, which is larger than what most people would need to do. And so if you have something smaller, your requirements are going to change. But what we did is we showed our cards and we provided the material quantities associated with this. So that if you're looking at a job with a general contractor and he's like doing some preliminary pricing, you can actually just feed him these material quantities and say, hey, if we wanted to do this, what would it be? Where would it benchmark through? And then you can apply that same idea to perhaps a smaller column bay. We also gave a worksheet that allows you to work through the different issues and identify the problems. Okay, what are you doing about floor penetrations? What are you doing about MEP attachments? How are you solving union issues and all these different issues, so that if you want to select this system and you want to look at it, it's a path there for you to understand the viability of it going forward. As part of our overall research project, we identified many recommendations early on, and one of the first things we said in our very first report was, can CLT replace composite metal decks in steel buildings? From our research, we said, okay, well, where do you get the biggest bang for your buck? And it's in the floor system for timber structures. And so it's something that we've always been kind of curious about. And I wanted to understand what that meant in terms of magnitudes. So I looked at another project of ours that recently completed, and I said, okay, well, this had just composite metal decks. What if we replace those metal decks with a composite timber floor using a 3-ply CLT? Well, that would be 200,000 cubic feet of CLT by just replacing the deck, and you're really not changing much about that building. 200,000 cubic feet of CLT is like more CLT than most CLT projects have in them, which is that one small move. And so it's a pretty effective way to increase timber usage in the market without having to go through a lot of the R&D. What are some of the other reasons why you might consider a steel and hybrid system? Well, there are all limits to all timber construction. We talked about that in the previous presentation, and this is something that we've studied ourselves. When do you reach that breaking point of an all timber structure? Well, there's a lot of engineering issues that happen and economics that you have to consider. One that we haven't talked about as much in this mass timber community is differential shortening. And it's a problem that really rears its head in steel and concrete buildings above 50 and 60 stories. But in a timber construction, if you look at how much the vertical structure will compress and how much it will creep and how much it will shrink, it's a real design issue that needs to be dealt with. So this is from our 42-story timber study, where we just took a look at how much are these things going to compress. And the thing you have to really consider is if you have a big, massive timber core and small little timber columns next to it, those timber columns will, elastically compress a lot compared to that core. And then whatever that amount of compression is, it will continue to move that way in creep, and it will shrink in the seasons. So you have to think about that. It's not really a structural performance issue, but it's really more of an impact to non-structural elements. So your cladding systems, for example, will they stay watertight if they're racking on the perimeter like this? Will it stay that way? Will you get cracking in your partitions? It's something to consider. Now, if you change it to a steel vertical structure, those issues essentially go away. So if you have a strong differential shortening issue, that might be a reason to consider it. Another is just vertical element sizes. If you're getting these real tall buildings and you're trying to maintain timber column locations only, they grow and they grow and they grow. At some point, they start impacting unit sizes, which can be a problem. If you're using structural steel, you could again just make the plates thicker to the point where you can make a solid steel column if you needed to. You could have an 80-story building supported on a 1 foot by 1 foot column. It's not going to the units. So you have to consider these things. And then lastly here, talking about the code issues. If we go into these ICC provisions and we're talking about how we do these different types of construction, we know that some of it's going to have to be encapsulated. You can't expose it all. So if you can't expose all of it, you might as well do what's right for the economics of the situation. So in conclusions, what is the goal of your project? What are you trying to do? Are you using timber for sustainability, aesthetics? What is your cost? What is your performance that you're trying to do? And a lot of times a hybrid system makes sense. In terms of how do you get there, a lot of people have a hesitation. It's like there's a lot of excuses. I had to use a concrete core. I had to do this. I wanted to, but I couldn't. But when we think about the overall sustainability of these projects, if you think about where timber is most effectively used, that's actually much more sustainable. Because if you look at a concrete core and trying to compete with timber, it takes a lot of timber to replace that concrete core. So in many ways, the more sustainable building is a hybrid solution that actually minimizes how much timber it takes to replace those other materials. Okay, thank you.